our next presenter is a person that you have heard a lot from. He is standing in front of you, waiting
And
for
he's a
his
computer
presentation. Didn't come out.
Can't quite figure out who that is.
All right, so I'm going to be telling you whenever this. I swear it's on. Like, okay, I had to click on it. Whatever.
Oh.
All right, I am going to be talking to you about a strange visitor from beyond the solar system. I was challenged about 4 months ago by Glenn Wilkins, who I don't think made it here tonight, to find somebody to give a presentation on how we figured out so much about Oumuamua so quickly. Well, I found me, so.
Yeah.
So this is as visually pleasing as my presentation gets. So what is Oumuamua? Who discovered it? Why is it called that? Where did it come from? Where is it going? And how do we know what we know about it? All right, without further ado, what is Oumuamua? It was first discovered in 2017 as an interstellar comet, as a comet, and within about 6 days they had figured out that it was probably an interstellar comet. But then it got close. Then it was coming away from the sun, and they didn't see any coma around it at all, and it looked like it had a crust around it, based on the color of it. And so they said, no, it's an interstellar asteroid. And then they started watching it recede away from the sun, and they said, but it's outgassing something, so it must be an interstellar comet. So it is the first object to have its classification switched from a comet to an asteroid, and by default, it's the first object to have its classification switched back
You should
to a
invent a
comet.
new name
Wow.
for it. Like,
I could. It's a comet-steroid. Comet-steroid. So it's a and in terms of the shape, what is it? It's a monolith. If anyone remembers this movie, this is so it's Oumuamua is kind of tumbling, like if you remember this iconic scene from 2001: A Space Odyssey. But it's maybe more like a space cigar, like a skyscraper-sized brown cigar that is tumbling through space. Except maybe it's a space pancake. So we actually don't know what shape it is, because all the telescopes that have ever pointed at it have only been able to see it as a single pixel. So everything we know about it came from that single pixel. So what can we know about, how can we get to this picture of it? And this picture might have some problems, like the outgassing probably doesn't look quite like that. So how do we know its size, shape, color, and rotation? So what we've been able to record with the various telescopes that have looked at it is a light curve as well as photometry data. So based on the models that we have taken, Oumuamua is about 800 feet long by 100 feet wide by 100 feet deep. So about the size of some of the skyscrapers in downtown Detroit. It's dark red. We know that from looking at the spectrum with the Hale telescope at Palomar and the Herschel telescope in the Canary Islands. The rotation rate has been inferred by looking at the frequency of the light curve dipping and rising. And the size and shape have purely been inferred by looking at how huge these swings are from bright and dim, and how violently truncated the dim part gets. Like, this looks like the end of something. But the thing is, it's hard to say whether it's the end of a cigar or the edge of a pancake. So we're still a little bit unclear about that, and it's not getting any closer. It's very quickly heading out of the solar system. So we're probably never going to know about this one, for sure. So this is one artist's rendition from a British, you may notice there's no attribution here, from a British newspaper that shall not be named. So this sort of puts it into scale. So this is on the high side of the estimate, so this is approximately, this is assuming it's about 1,300 feet tall, rather than 800 feet tall, but you know, somewhere in this range. So what we do know for sure is that Oumuamua is spinning in a very excited state. It has a pronounced wobble that adds to the weirdness of this, like this light curve is also wobbling, and that's because of the rotation of the object. It's not spinning smoothly like a planet turning or as it spins in a normal object, in a normal axis. It's more swinging around like something in the movie Gravity, where, you know, there's just no direction, it's just totally random. The primary spin axis is close to the long axis. They think it rotates about every 55 hours. And it simultaneously is precessing and nutating every 8.67 hours. So picture a very wobbly, badly thrown football. So one thing we know pretty solidly is that Oumuamua is not a space station. So I don't know who's read Rendezvous with Rama, but not to spoil it or anything, but we have this long tumbling object enter the solar system, and it turns out to be interstellar, and a bunch of astronauts intercept it and study it. So that object is way, way larger than this is. And just to make sure that because it was such a weird object, we wanted to find out if it had any like electromagnetic radiation, if it was transmitting anything. And so the SETI telescope actually looked at it for about 2 days. They actually got the Green Bank radio telescope to look at it for 6 hours. Didn't hear anything at all from it. So it's a dead object. It's definitely a natural object. So the funny thing is, so Rendezvous with Rama, it's just funny how things match up. So in Rendezvous with Rama, it's a 20-kilometer diameter, 54-kilometer long object, and spinning at a somewhat similar rate, although in a different direction. So it's just funny how life imitates art at times. So who found Oumuamua? So we actually have some semi-local connections. So Dr. Rob Warrick was part of the team, but he technically is the discoverer of it as part of the Pan-STARRS program. And he discovered it in data on October 19th, 2017. There were 2 pre-covery observations found in Catalina Sky Survey images on October 14th and 17th. So it could have been our former member who had retired by then, so Rick Hill worked at the Catalina Sky Survey for about 25 years and has named a whole bunch of asteroids. He might have gotten the chance to name this if he had worked there a little longer. So the telescope it was found with is Pan-STARRS 1. One of our members in attendance here has observed Pan-STARRS 1 rather closely. It's on top of Mount Haleakala on Maui. And so John Blum actually gets to observe from up there fairly frequently. So
observe from the outside of
not
from
from inside the telescope, but he gets to observe the telescope, so not with the telescope. All right, so why is it named Oumuamua?
Yeah.
So Oumuamua is Hawaiian for scout, and it is kind of another neologism. So the word O means reach out for, and moi means first, and repeating it for emphasis means like really, really first. So it's literally like first distant messenger.
Really, first.
And it was chosen by the Pan-STARRS team with guidance from Kaiju Kimura and Larry Kimura of the University of Hawaii at Hilo on the Big Island, which I think I think that's where the Pan-STARRS control systems are. So the IAU had kind of a dilemma because they claim ownership over naming everything in the sky. So what do you call the first object of its kind? Do you call it according to its original terminology? Is it just a comet? So originally it was called Comet 2017 U1, Then they reclassified it as asteroid 2017 U1, and then they said, well, it's the first interstellar object, so it's 1I. And then they said, well, there might be other ones, so we'll make it 1I 2017 U1. And so, even though Oumuamua is not formally recognized by the IAU nomenclature, you don't get to name stuff unless it's asteroids, people are still obviously calling it that. So the common name for it is 1I 2017 U1 Oumuamua. So, where did it come from, and where is it going? So, I'm going to switch to... So, basically, it came from Vega, and it kind of has been spiraling towards us for years and years out of the constellation Lyra, and spun down. It hit its closest point to Earth on October 15th of 2017, and now has started spinning away through, so this is March of 2018, March of 2019. It's going to be going out through the great square of Pegasus into the great wide open, because there's no Milky Way out there. So it may be, yes sir?
Is the spiral due to the Earth's motion around the sun?
Yes.
Is our perspective?
Correct. Yeah, so this is just our perspective in the sky. So this is, you're seeing the yearly rotation of the Earth here, the revolution of the Earth around the sun. So, did it come from Vega? Not really, because it would have taken 600,000 years for it to get here, and Vega wasn't there 600,000 years ago. Vega is moving quick as well, and Vega is very close to us. The other interesting thing about Oumuamua is that the velocity, its relative velocity to the solar system is very standard velocity for other space junk, like brown dwarfs and other stuff in the region of the sun, which is called, that rate of rotation or that rate of movement through the galaxy is called the local standard of rest. So it may have been caught up in the ordinary flow of the Milky Way for billions of years. And it might have just been drifting until it had this exciting trip through the solar system and then got boring again. So, but yeah, and it's going to be going out through the great square of Pegasus, and obviously, the stars that compose Pegasus are going to be moving too. So this is like the north side of the Milky Way. That's kind of looking out from the top of the Milky Way, so this is the Milky Way. So in this direction, it could exit the galaxy, but I don't think. It would be a very, very, very long time before it ever did.
Did it get a gravity assist at all? Did it speed?
It did, so it got a huge gravity assist from the sun, so the sun accelerated it. So, and what you'll see here, so this is its close approach through the solar system. So 729 comes in past the Mars orbit in about a week. So about every week it's closing the gap between planets that are very far apart. So traveling an astronomical unit every 2 weeks essentially. So August 5th it crosses Mars's orbit. August 19th it crosses Earth's orbit, actually probably August 15th or so. August 26th passes by Venus. Its closest approach to the sun is on September 9th of last year, and it gets gravity assist from the sun. We don't recover it until it's past the sun. So if it were to have heated and started putting out a coma, we would have seen it in cometary outburst, and we didn't see anything notable coming from it. And this is sort of the nearer term. So it really came from way above the plane of the solar system, arced around the sun, and got shot out on the other end. So this is what's called a hyperbolic orbit.
That's a very smart thing to do for a dumb rock.
So so what's interesting is that its closest approach to the sun was 0.255 AU. It was 17% closer than Mercury to the sun. And its closest approach to Earth was 0.16 astronomical units. So it was a pretty, if we had known it was coming sooner, Who knows? We might have been able to get some better pictures. Probably not. So, how long is it going to take to leave the solar system? It had this one super cool year, you know, really in the main plane of the solar system. How long is it going to be in the solar system, inside the Oort cloud? About 20,000 years from now. So it has probably spent it will probably spend about 40,000 years of its lifetime in our solar system. All right, so here's the harder part. How do we know its orbit? So I'm going to be talking about eccentricity, and I'm not talking about people who sing Broadway show tunes during their presentations. So the eccentricity of an ellipse or an orbit determines what kind of orbit it's going to be. So if there's no eccentricity in a conic section, which is, you know, a conic section is if you take a cone and take a slice through it. Whoa. No. Basically, if you take a cone and draw a path through it, if you draw a path arcing down like this, you get an ellipse. If you draw a line straight through it, you get a perfect circle. If you draw a line cutting through it at an edge, you get a parabola. And if you draw a straight line down between two cones, you get a hyperbola. So, let's see if we can catch up there. So, the orbital eccentricity of Oumuamua's hyperbolic orbit was 1.2, which is the highest ever observed. Only comet C1980 E1, that's the only object that has ever been seen with a hyperbolic orbit prior to this. So the eccentricity of comet 1980 E1 was 1.057. So it was basically, it was just a tiny little bit off being a parabolic orbit. Let's see if this starts working. Okay, good. All right, so how do we know its orbit? Well, going back through the history of figuring out orbits of weird things, we can get some good ideas on what we should do. So, you may recall that the orbit of Mars was a puzzle that vexed astronomers from Ptolemy all the way through Tycho Brahe. And it was not until Johannes Kepler actually was able to put the math behind Mars's motion that we figured out what Mars's orbit was, or even where Mars was going to be in the sky. And you may also recall that the asteroid, the minor planet Ceres, was also an extremely difficult object to find. Astronomers found it, then it went through the daytime, and then when it was in the nighttime sky again, they couldn't find it. And it took quite a long time before they were able to actually recover it. So, we'll talk very briefly about Kepler's laws. So Kepler's laws are, the important ones are that all planets move in elliptical orbits with the sun at one focus. So basically, in an ellipse like this, the sun is going to be right here. A line that connects the planet to the sun sweeps out equal area in equal time. So basically, when a planet is very far away from the sun, it's moving very slowly. When it's very close to the sun, it's moving very quick. So in a given, like in an Earth day, no matter where in the orbit it is, the area of the angle drawn out by the planet's movement through the solar system is going to cover the same area. And the square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. It's not quite so relevant. But this second law here is it helps Kepler crack the mystery of Mars, because he figured out that as Mars got closer to the sun, it sped up, and basically allowed him to put all the pieces together. Similarly with Ceres, Gauss, so basically Kepler didn't really have the background in conic sections that the later, building on Newton's work, building on Kepler's work, other astronomers were able to continuously develop the mathematical tools they could use. And so basically there are 6 orbital elements that define a Newtonian orbit. So you have 2 parameters that basically determine the plane of the object's orbit relative to Earth's orbit. You have to have the scale of the orbit, you have to have the eccentricity of the orbit, or the shortest distance to the center of the solar system, the center of the sun, and the tilt of the axis. So those are 5 things. And you need a single time when the object was at a particular point in its orbit. So to get these 6 orbital elements to figure out what an orbit is, you only need to get 3 observations. So Johann Friedrich Gauss was able to take 3 observations of Ceres and actually work out all of the angles here to figure out exactly what Ceres' orbit was. The astronomer who took the observations took 22 observations over 41 days. Gauss started with 3 observations, spent over 100 hours calculating it, and in December 1801, astronomers were able to use his calculated values to recover it. So when Vesta was discovered, it only took him 10 hours to calculate it, and he could calculate the orbit of a comet within an hour by the time he was done. So we're not going to get too much into the math, but you can kind of see the areas swept out by the orbit are proportional to elapsed times. That's Kepler's second law. You can apply it in other circumstances. And unfortunately, the mathematical processes at work are beyond the scope of what we're going to cover in meetings. But the important thing, the important piece of math here is if you've ever, I don't know who else did modeling, did like a business class or something. You have some curve fitting that you need to do, and you want to find a curve that fits these data points that you have. So the common method is called the method of least squares, and that is pretty much the approach that that Gauss took. You also may be aware of a Gaussian distribution, which is the familiar bell curve, and that was also sort of a side effect of the way that he calculated the orbits of unfamiliar bodies. So, in the present day, how much further have we gotten from Gauss? So, it actually took them 6 days worth of serious observing with basically every free telescope in the world to be able to calculate an orbit that they believed in. They basically tried and rejected 2 different elliptical orbits. They wanted to assume that it was a solar system body. They didn't want to assume it was the most exciting thing possible. So they tried 2 different elliptical orbits and really tried to make the data fit. And then finally they decided it had to be a hyperbolic trajectory. But even with 6 days of serious observations from the best telescopes in the world and off the world, the Minor Planet Center still said, unless there are serious problems with much of the astronomy, like there's so many conditionals here, they were so afraid to say that it was interstellar. If further observations confirm the unusual nature of this orbit, this object may be the first clear case of an interstellar comet. So even though we've come a long way in being able to measure things, even though we've come a long way in terms of being able to run numerical simulations with supercomputers, stuff moving in space is hard to predict because of the various gravitational tugs on things. Uncertainty in a calculated orbit never reaches 0. We can track an asteroid for 100 years and we won't be able to make uncertainty go to 0, much less an object like this that's coming in from literally out of left field. So I have never read so much for a 20-minute presentation. But there's a ton of super interesting information about this. If you would like to go deep into the mathematics, I have some documentation on the classical methods for calculating orbits, the more modern methods, as well as a presentation put together by some undergraduates at Berkeley that is super useful. Yeah, if you are interested in hearing, if you're interested in digging into this anymore, I'd be happy to share some resources. So with that said, any questions? Yes.
So this object is tumbling end over, like a cigar tumbling end over end, coming through the galaxy.
Yep. So it probably got flung out of its home solar system in a really exciting way. And yes.
When an object is rotating, tumbling, it would, over time, as I recall from mechanics, assume a minimum, it would assume an axis and a rotational mode, which would conserve the inertia, the rotational inertia.
Yeah, there's conservation of angular momentum through here. That's the
fact that this thing is tumbling, and it has been for centuries or eons, isn't that is there any speculation as to why it has not assumed a...
So they think it, I mean, they do think it does have a period. It's just a really weird period. You know, it's tumbling like this in this direction, but it's also precessing, and it's, whatever that word is. So it's basically moving in 6 different axes in apparently a fairly stable mode, but it looks very chaotic to us because we're just watching the light reflect.
It just seemed like it would settle into a mode that conserves its inertial energy.
But there's nothing, there's no forces acting on it. I mean, it is moving through vacuum.
Well, momentum.
Yeah.
I mean, it's...
Well, no, but I mean, like whatever weird spin it had put on it when it was in some solar system, it's conserving that, and unless it gets really close to some body or hits, you know, if it hits enough bodies, maybe it could be knocked back into some kind of more stable orbit. But right now, this is stable for it. It's, you know,
I'm not talking about the orbit. I'm talking about it.
I mean the
Rotation.
the tumbling motion. Like it has reached some stable point, but with regards to like its view of stability is very different from ours.
Yeah.
So, yes, Riak.
I don't think we have any chance of seeing anything like this, but what magnitude did they say was observed at, or when it comes back from behind the sun, what would it be?
Oh, it's already, I mean,
Right.
by the time we saw it for the first time, it had already passed perigee, or perihelion.
All right. And what magnitude?
I think it was down at like 14. It was a very
14.
dim object.
So actually, it's not that.
I mean,
Not
when
that dim.
it was recovered, which it still was
Yeah.
inside the orbit of Mars. So
Okay.
You said that they looked for electromagnetic
yes,
stuff coming off, radio signals or something like that, and they didn't find any after a few days and stuff. That doesn't mean it's a rock. They could have turned off their radios or...
Yeah.
it's like, oh my God, that was.
You know, I mean,
Their batteries were out.
the batteries could be out.
They were
Yeah.
So
So
that's, I mean, that's a fair point. So we do know from spectral analysis that it is iron heavy. There is a lot of metal
well, there
involved.
you go.
The albedo of it, as far as we can tell, like it's hard to get a good model of the albedo of it because we don't even know what the shape is. But it looks a lot like an asteroid, a very metal-rich asteroid to us. So, and they do think, so I said that the outgassing in this picture is a little bit wrong. So what they kind of think is that outgassing on this body consists of like it kicking off sand grains. Like it's not really putting off, it's not really evaporating, it's really like depositing these single bits of rock or dust at a time.
Breadcrumbs.
Yeah, breadcrumbs. Yes, sir.
Is this what our scientists are predicting that will come close to hitting the Earth in about 30 years?
No. This is. I mean, this was our only visit that we'll ever get from it. It's gone. In 20,000 years, it will be out of the solar system. But that said, the fact that so quickly, now that we have telescopes trained on almost all of the sky at one time, and in fact with the LSST coming on, who knows what we'll find. Like, we may find these to be much more common than we had ever dreamed. This was just the first one that we found. And our technology and the optics that we have on the sky keep getting better. So it could be, it's not inconceivable that within my lifetime we might actually be able to do some kind of sample return from some object like this. Like, if we had known that this was coming 20 years ago, it was obviously invisible, it was too far away. But if we had known that something like this was coming, we could have probably gotten the spacecraft out to point to astronomical units. I don't know. Maybe not a sample return spacecraft, but maybe something that could send a signal back. Yes, sir?
How close did we come to missing this altogether? I mean, it was discovered by these guys in the Pan-STAR survey, but was it an easy?
Like I said, the Catalina Sky Survey had picked it up. So if Rick Hill had been there, he would have found it.
But they didn't recognize, it wasn't significant enough signal or something for them to call it out as significant.
Well, I think they maybe had not even gotten to the data yet, because I think Pan-STARs, if you have noticed, find stuff really fast.
That's where the LSST would have probably picked this thing up.
Right. Yeah, so if we had been able to pick it up earlier, who knows what we could have done.
How long before it leaves the solar system?
20,000 years.
It's a fine solar system.
So that means it'll be out of the Oort cloud.
It's left the inner,
Oort
solar system already.
Yeah, it's left the inner solar system. Like, I don't think it's to the heliopause yet, but it's getting there fast. I mean, it's going way faster than like Voyager. So.
Is it big enough to?
Like Sigmund Freud once said, sometimes a cigar is just a cigar.
All right.
I'm not going anywhere.
All right.
Yes.
You know how fast it was traveling in the vicinity of the Earth?
I have seen the number. I don't have it. I don't think I actually noted it.
As fast as it's going, I don't think, even if we'd have known.
Yeah, we couldn't have gone into orbit or anything.
Got going near it, we could have maybe crossed its path.
Yeah.
It would have been nice to, pick up, if we could pick samples up behind it, or even if we had been able to get closer observations of it.
Anything like half an astronomical unit per day,
Yeah.
way faster
No,
than
that's true.
anything we've ever done.
Well, it was an astronomical unit every 2 weeks, right?
2 weeks.
But still way faster now. Yeah. Yes. Okay. Any other questions? All right. Well, thanks so much. And,